Right now, somewhere in the depths of your social media feed, someone is probably sharing a headline that claims scientists just discovered proof of alien life existing somewhere beyond Earth. 5 minutes ago, a new video dropped claiming James Webb detected a signal from beyond our solar system. The thumbnail is dramatic. The thumbnail always is. The title probably includes exclamation marks and words like shocking, just happened, or scientists confirm. But before you get swept up in the excitement, before you start imagining what extraterrestrial life might look like, or whether we're about to make contact with an intelligent alien civilization that could communicate with us, you need to understand something absolutely crucial about this story. Everything you think you know about what was actually found is probably wrong, or at least massively incomplete, in ways that fundamentally change the meaning of the entire discovery. What James Webb actually detected coming from beyond our solar system is not a radio signal in any conventional sense. It's not a beam of light being intentionally transmitted toward us. It's not anything artificial at all. What was detected is something far stranger, something far more subtle and deeply fascinating, and something that has launched one of the most intense scientific debates in recent memory. It's a chemical fingerprint, a molecular signature hidden inside starlight, a pattern of absorption in a spectrum of light. And on Earth, this particular fingerprint is only ever reliably produced by living things, by biological organisms going about their metabolic business. But here's the critical part that headlines conveniently leave out entirely. Multiple teams of independent researchers have spent the last year running their own careful analyses of the exact same raw data. And most of them are not convinced that the original detection is real. Some say it's nothing but noise. Others say it's a different molecule entirely. Welcome to the messy, complicated, genuinely fascinating reality of how science actually works when the stakes couldn't possibly be higher. Before we dive deeper into what was actually found, let me explain the instrument that made this entire incredible debate possible. The James Webb Space Telescope launched in December of 2021, and it now orbits approximately 1.5 million kilometers from Earth at a gravitationally stable location in space called the second Lagrange point. Think of it as a perfect perch, far enough from Earth to avoid our thermal interference, yet still tethered to our planet by gravity in a precise, stable orbit. Webb is an infrared telescope, built specifically to detect faint heat signatures and incredibly stretched out light from extremely distant, extremely faint objects deep in space. But here's the thing that makes Webb genuinely revolutionary. While it was designed primarily to study the earliest galaxies in the universe and distant star-forming regions, it turned out to be exceptionally good at a completely different kind of job. Studying the atmospheres of planets orbiting other stars, worlds we've never sent spacecraft to, places we may never actually visit in person. This is where the real magic happens. When a planet passes directly in front of its host star from our perspective on Earth, a moment that astronomers call a transit, something remarkable occurs. A small fraction of the star's light passes straight through the planet's atmosphere on its way toward us. As that light travels through, different gases in the atmosphere absorb very specific, precise wavelengths of light, carving tiny but measurable dips into the overall spectrum of light that Webb eventually receives back on Earth. By carefully measuring exactly where those dips appear and how deep they are, scientists can work backward and figure out which specific molecules are present in a distant planet's atmosphere and roughly in what quantities, all without ever needing to send a single spacecraft anywhere near the planet itself. This technique is called transmission spectroscopy, and it's exactly how every single remarkable result we're about to discuss was actually obtained. Let's start with where this signal is actually coming from. The planet at the center of this story is called K2-18b, and it sits roughly 124 light-years away from Earth, nestled inside the constellation Leo. It orbits a small, cool, quiet red dwarf star, and it completes one full trip around that star in just about 33 days. Despite having such a remarkably short orbit, K2-18b actually sits quite comfortably inside its star's habitable zone, that crucial region around a star where temperatures could theoretically allow liquid water to exist on a planet's surface or beneath its clouds. This is possible because red dwarf stars are so much cooler and dimmer than our own sun that their habitable zones sit much closer to the star itself. Now, in terms of size, K2-18b is considerably bigger than Earth. It's roughly 2.6 times Earth's radius and about 8.6 times Earth's mass. This puts it into a category of planet that we don't actually have any direct examples of anywhere in our own solar system, something scientists broadly refer to as a sub-Neptune. Essentially, it sits somewhere between the size of rocky Earth and the size of much larger ice giants like Neptune. Back in 2019, early observations of K2-18b using a combination of the Hubble Space Telescope and other instruments suggested the planet might have water vapor in its atmosphere, sparking early excitement about its potential habitability. But that excitement was tempered when later more careful analysis called that original water vapor detection into question, suggesting it might have actually been methane instead. This was an important early reminder that this particular planet has a long history of exciting announcements, followed by more cautious, more careful scientific double-checking. Then, in 2023, the James Webb Space Telescope turned its remarkable instruments toward K2-18b and delivered a much clearer, higher quality picture than anyone had seen before. Webb confirmed the presence of methane and carbon dioxide in the planet's atmosphere while also finding a surprisingly low level of ammonia. This particular combination of chemicals matters enormously because it lines up almost perfectly with a theoretical model proposed by astrophysicist Niku Madhustin at the University of Cambridge. Madhustin had described a type of planet he named a Hycean world, short for hydrogen and ocean. A Hycean world, in this fascinating model, would have a thick, hydrogen-rich atmosphere sitting above a deep, planet-wide ocean of liquid water. The low ammonia levels matter specifically because ammonia dissolves easily into water. Finding very little of it in the atmosphere is consistent with the idea that a massive ocean underneath could be quietly absorbing it, pulling it out of the atmosphere and into the water below. This 2023 result alone was already a significant discovery in exoplanet science, marking the first confident detection of carbon-based molecules in the atmosphere of a habitable zone planet around another star. But the moment that truly launched K2-18d into worldwide headlines came in April 2025. Using Webb's mid-infrared instrument called MIRI, Madhustin's team announced they had detected chemical fingerprints, matching either dimethyl sulfide, known as DMS, or a closely related molecule called dimethyl disulfide, known as DMDS, inside K2-18b's atmosphere. Why did this cause such an enormous stir? Because on Earth, DMS and DMDS are produced almost exclusively by living organisms, primarily marine phytoplankton and certain types of marine algae. There are very few known ways to naturally produce these particular molecules without biology being involved somewhere in the process. A University of Cambridge press release described this as the strongest evidence yet that life might exist on a planet outside our own solar system. The implications were staggering. Possible microbial life, 124 light-years away, detected through chemistry alone. Headlines around the world ran with it almost immediately, and it's easy to understand why. This was one of the most tantalizing, most headline-grabbing results in the entire history of humanity's search for life beyond Earth. But here's the critical part that most headline-driven coverage conveniently leaves out entirely. The scientific community's response was immediate, cautious, and in many cases openly skeptical. Just days after the announcement, Jake Taylor, an astrophysicist at the University of Oxford who studies exoplanet atmospheres using Webb, ran his own independent reanalysis of the exact same raw data. His conclusion was blunt and direct. He found no statistically significant evidence supporting the DMS or DMDS detection at all. This wasn't a lone dissenting voice either, and that's crucial. Over the following months, multiple independent research teams, including researchers named Luke, Wellbanks, Schmidt, and Stevenson among others, each ran their own separate analyses of the same raw data, using different modeling approaches and different analytical assumptions. Several of these independent studies reached the same conclusion as Taylor. The supposed DMS or DMDS signal was sitting right at the edge of the instrument's noise floor, meaning it was statistically indistinguishable from random measurement noise rather than a confident detection of any specific molecule. One especially thorough follow-up effort expanded the search dramatically, testing the observed spectrum against a library of 661 different candidate molecules individually, attempting to systematically identify every plausible chemical explanation for the observed pattern rather than focusing narrowly on DMS and DMDS alone. This study also checked the robustness of the original claim using 3 separate independently built analysis codes running on the exact same underlying dataset. One particularly detailed study published later in 2025 dug even deeper into exactly why different research groups kept getting noticeably different answers from analyzing the very same underlying data. This is an important question in its own right, because it goes directly to how reliable and repeatable the original claimed result actually was. That study found something crucial. The apparent DMS or DMDS signal appeared to be an artifact created by a specific technical choice in how the raw data was grouped together for analysis, a process called binning. Researchers tested many different reasonable binning configurations and found that only a small fraction of those configurations, roughly 1 in 8, actually produced results supporting a DMS or DMDS detection at all. In other words, depending on exactly how you sliced up the same raw numbers, you could either find weak hints of these molecules or find nothing at all. That is a serious red flag in careful scientific analysis, the kind of finding that makes scientists extremely cautious about claiming discovery. That same study also found that other completely different molecules, including one called ethylene and another called chloroethane, fit the observed data at least as well as DMS or DMDS did, sometimes even better. This means the original signal, even if it is real and not just noise, cannot currently be confidently attributed to any one specific molecule. When multiple different molecules can explain the same data equally well, you don't have a detection. You have ambiguity, and ambiguity is exactly what scientists spend their careers trying to eliminate. In July 2025, a separate NASA study added yet another layer to this ongoing scientific back and forth. This team set out specifically to compare results across multiple different research groups using multiple different modeling approaches, attempting to figure out which conclusions about K2-18b's atmosphere were consistent no matter which method you used and which conclusions changed depending on the specific assumptions each team made. Their findings painted what researchers described as a genuinely nuanced picture. They confirmed with reasonably strong confidence across nearly every method tested that K2-18b really does have a water-rich atmosphere, with water potentially making up as much as half of the atmosphere's total mass, along with confirmed methane and carbon dioxide. However, this same NASA study found no conclusive evidence supporting the presence of DMS specifically, essentially tempering, without completely ruling out the excitement generated by the original April 2025 announcement. So where does all of this leave us? As of the most recent, most careful, most independently checked analysis available, the honest answer is that K2-18b almost certainly does have a genuinely interesting water-rich atmosphere containing methane and carbon dioxide. This chemical combination remains scientifically consistent with the Hiceian world hypothesis first proposed by Mattiston. But the specific headline-grabbing detection of DMS or DMDS, the part of the story most closely associated with the phrase possible sign of alien life, currently does not meet the rigorous statistical standard of evidence the scientific community requires before confidently announcing a biosignature detection. Multiple careful independent reanalyses of the exact same raw Webb data have consistently found that the supposed signal is either statistically insignificant, likely explainable by other non-biological molecules, or dependent on specific, somewhat arbitrary technical choices made during the data analysis process. This entire episode is actually a genuinely valuable case study in exactly how careful, rigorous science is supposed to work. Even when the initial headlines get ahead of the underlying evidence, a research team makes a bold, exciting claim based on genuinely real data. Independent researchers immediately reanalyze that same data using different methods to check whether the result holds up. Some groups agree, some disagree, and everyone publishes their reasoning openly so other scientists and eventually the public can follow exactly how each conclusion was reached. Astrobiology, the scientific field dedicated to studying the possibility of life beyond Earth, has been through cycles like this before, and each time the process of open scientific debate and independent verification has proven essential for separating a genuinely important discovery from a statistical false alarm. Researchers involved in the K2-18b debate have pointed out that this situation closely echoes two earlier cases in the history of astrobiology. In 2020, a research team announced a potential detection of phosphine gas in the thick clouds of Venus, initially framed as a possible sign of microbial life floating in that planet's atmosphere. Follow-up studies identified plausible non-biological explanations for the same spectral signal, including possible instrumental artifacts and alternative sulfur-based chemistry that didn't require biology at all. Decades earlier, in 1996, a team of scientists announced they had found what appeared to be fossilized microbial structures inside a meteorite that had originated from Mars, a claim that generated enormous excitement at the time, even prompting public remarks from the sitting President of the United States, before later, more careful research demonstrated that the specific mineral structures being used as evidence could form through completely ordinary non-biological geological processes as well. Over the following years of careful, methodical follow-up research, scientific confidence in that original claim gradually eroded. It's worth spending more time on the Hiceian world idea because it's central to why K2-18b generated so much excitement in the first place, well before the DMS debate ever started. Mattiston first proposed the Hiceian concept as a way of expanding where scientists might reasonably search for habitable conditions beyond Earth, potentially finding life in places completely unlike anything we see in our own solar system. For decades, the search for potentially habitable exoplanets focused almost entirely on finding rocky, Earth-sized planets sitting at just the right distance from their star, essentially looking for direct Earth twins. It made intuitive sense. Life evolved on Earth, so we should search for Earth analogs. The Hiceian concept revolutionizes this thinking by opening up a much larger category of candidate worlds, sub-Neptune-sized planets, larger than Earth but smaller than Neptune, that could theoretically host enormous planet-spanning oceans of liquid water underneath a thick, hydrogen-rich atmosphere. Picture it. A world where the entire surface is covered by a deep planetary ocean, hundreds of kilometers deep in some places, all of it protected and warm by a thick atmosphere of hydrogen and helium above. Because these planets can be significantly larger and could potentially orbit at a wider range of distances from their star while still maintaining livable ocean temperatures beneath their thick atmospheres, Medustin's team has argued that Hycean worlds could realistically be common throughout the galaxy, perhaps far more common than Earth-like rocky planets. Importantly, because of their larger size, they tend to be easier for telescopes like Webb to study in detail than small, rocky, Earth-sized planets, which produce much fainter signals when starlight passes through their comparatively thin atmospheres. K2-18b became the flagship test case for this entire revolutionary idea. It's the first candidate world where scientists actually had enough high-quality atmospheric data from Webb to meaningfully test the concept against real observations, rather than just purely theoretical models. Let's spend a meaningful moment on what these sigma values and the numbers scientists use to describe detection confidence actually mean, because they come up constantly throughout this entire story and they're genuinely important for understanding exactly why the scientific debate has dragged on so long. In science, a detection described as 3 sigma means there's roughly a 1 in a few hundred chance the observed pattern could have appeared randomly just from ordinary noise in the data rather than reflecting something real. That might sound reasonably convincing on its own, but by the standards astronomers and physicists generally require before confidently announcing a genuinely new discovery. Especially one as significant as a potential biosignature, 3 sigma usually isn't considered strong enough evidence on its own. Many major discoveries in physics and astronomy, including the historic 2012 discovery of the Higgs boson, weren't officially announced as confirmed until researchers reached a 5 sigma confidence level, corresponding to roughly a 1 in a few million chance of the result being random noise. The original April 2025 DMS and DMDS announcement from Madison's team sat right around 3 sigma confidence, which explains both why the team felt genuinely confident enough to publish and publicize the result, and why so many other researchers immediately treated it as an intriguing but far from settled finding that absolutely required independent verification before anyone should treat it as confirmed. Let's talk about why finding a definitive, universally agreed upon biosignature is such a genuinely difficult scientific problem in the first place, and why so many careful, well-trained scientists can look at the exact same numbers and still walk away with different conclusions about what those numbers actually mean. Many of the molecules scientists consider promising signs of life can, at least in principle, also be produced through completely non-biological chemical processes. Things like volcanic activity, reactions between a planet's atmosphere and its surface rocks, exposure to intense radiation from the host star, or chemical reactions triggered by impacts from comets and meteorites. At the same time, genuine biological activity on a planet could theoretically be completely hidden from telescopes like Webb, masked by cloud cover, diluted by low production rates, or simply produced in quantities too small for current instruments to reliably detect from 124 light-years away. Because of this fundamental ambiguity, most astrobiologists researching this field have moved away from searching for any single silver bullet molecule that would instantly prove life exists somewhere. Instead, the field increasingly focuses on looking for entire combinations of molecules that would be jointly difficult to explain without some form of biological activity, essentially building a much stronger circumstantial case out of multiple independent pieces of evidence rather than betting everything on one single potentially ambiguous detection. Now, let's talk about the other half of this headline, the part specifically mentioning a signal being detected, because it's genuinely worth being completely clear about exactly what kind of signal we're actually talking about here, especially since plenty of online content tends to blur this distinction on purpose. What Webb detected on K2-18b is not, and never was, any kind of transmitted signal in the ways most people picture when they hear that word. It is not a radio broadcast. It is not a beam of light being sent toward us on purpose. It is a spectroscopic signature, meaning astronomers analyzed how starlight from K2-18b's host star gets filtered as it passes directly through the planet's atmosphere during a transit when the planet crosses in front of its star. From our point of view, different molecules absorb very specific, precise wavelengths of light, leaving behind a kind of chemical fingerprint embedded in that filtered starlight. Webb's instruments are sensitive enough to detect and measure those extremely subtle absorption patterns, and scientists then work backward from that pattern to figure out which molecules are likely present in the atmosphere. That is genuinely remarkable technology, but it is fundamentally different from detecting an intentional signal being broadcast by some kind of intelligent civilization. In fact, in March 2026, a completely separate research team directly addressed that exact question, specifically checking whether K2-18b showed any evidence of an intentionally transmitted signal at all, evidence of any attempt at communication. This team conducted what's called a technosignature search using 2 powerful radio telescope arrays, the Carl G. Jansky Very Large Array, usually just called the VLA, and the Meerkat Array located in South Africa. Technosignatures are observable, measurable signs of technology, the kind of evidence a genuinely intelligent, communicating civilization might deliberately leave behind for others to detect. Most commonly imagined as narrowband radio transmissions, since a very narrow, precise radio frequency is considered an efficient, deliberate way for any civilization to try to signal its presence across interstellar distances. Narrowband signals are interesting because they're distinctive. Natural astronomical objects like pulsars and supernovae produce broad-spectrum radio emission. A narrow, focused signal is a hallmark of engineering, of deliberate intention. If an alien civilization wanted to announce their presence to the cosmos, a tight radio beam is exactly what they might use. The VLA observed the K2-18 system across multiple separate days between late September and late December of 2023, while Meerkat contributed 3 additional observing sessions that same year. Together, they covered at least one complete 33-day orbit of the planet around its star. This combined search scanned an extremely broad range of radio frequencies from 544 MHz all the way up to 9.8 GHz, a noticeably wider range than most previous technosignature searches had covered, with sensitivity capable of picking out transmitters up to 1,000 times weaker than earlier searches could detect. After processing an enormous amount of carefully collected data, more than 20 million individual detected radio signals from the VLA observations alone, the research team applied a careful filtering process. Since K2-18b is actively orbiting its star, any genuine, deliberately transmitted signal originating from the planet itself should show a very specific, predictable shift in frequency over time. By the planet's own orbital motion, similar to how the pitch of a passing ambulance siren changes as it moves toward and then away from you. Signals that stayed perfectly fixed in frequency across multiple different observing days without that expected shift were ruled out as likely originating from human-made technology here on Earth, radio interference from satellites, cell towers, or other terrestrial sources, rather than from anything actually located in the K2-18 system. After applying this filtering process across the entire dataset, the research team found no transmissions consistent with an artificial technological origin coming from the K2-18 system. So to be completely clear and honest about this entire story, no radio signal, no intentional transmission, and no confirmed evidence of extraterrestrial intelligence has been detected from K2-18b. What has genuinely been detected, confirmed by multiple independent research groups using different methods, is a water-rich atmosphere containing methane and carbon dioxide, sitting on a planet orbiting comfortably inside its star's habitable zone. What remains a genuinely unresolved, actively debated scientific question is whether that same atmosphere also contains dimethyl sulfide or a closely related molecule. Chemicals that, if their presence were ever confirmed with much stronger statistical certainty, would represent one of the most significant potential biosignature detections in the history of astronomy. Precisely because there currently isn't a well-established non-biological way to explain how large amounts of DMS could accumulate in a planetary atmosphere. This is exactly why scientists working on this case have consistently emphasized that more observations are needed before anyone can draw a truly confident conclusion either way. Because K2-18b happens to transit its star relatively frequently, completing an orbit roughly every 33 days, astronomers have the opportunity to schedule additional Webb observing time specifically to gather more data, hopefully pushing the statistical confidence of any detected signal, whichever molecule it eventually turns out to be, well beyond the currently disputed range. Some researchers involved in this ongoing debate have suggested that fully resolving this particular question may ultimately require the next generation of space telescopes, instruments even more sensitive than Webb, specifically designed with exoplanet atmosphere characterization as a primary scientific goal from the very beginning, rather than as one application among many for an already extremely busy observatory that also has to split its limited observing time between early galaxies, star-forming regions, black holes, and countless other scientific priorities across the entire astronomy community. NASA has already begun early planning stages for a future mission sometimes referred to as the Habitable Worlds Observatory, envisioned as a dedicated successor specifically built around the goal of directly imaging and characterizing potentially Earth-like planets around nearby stars, though that mission remains years away from launch and wouldn't be expected to gather its first meaningful data until sometime in the 2030s at the earliest. For now, K2-18b remains one of the single most closely watched, most scientifically significant exoplanets known to astronomers anywhere. A genuinely fascinating world with a confirmed thick, water-rich atmosphere sitting at a comfortable temperature range inside its star's habitable zone, orbiting a small, quiet red dwarf star 124 light-years from Earth. Whether that atmosphere also happens to contain a genuine chemical signature of active, ongoing biological life remains an open, actively contested scientific question, one that could realistically be resolved with several more years of careful, patient, independently verified observation, rather than through a single dramatic headline claiming the mystery has already been solved. It's also worth remembering that even if DMS or DMDS is eventually confirmed with much stronger statistical certainty, that alone still would not count as absolute definitive proof of life, since scientists would still need to rule out every plausible, non-biological explanation first, a process that could easily take years of additional dedicated observing time, laboratory experiments here on Earth, and careful theoretical modeling before the broader scientific community would be willing to describe the case as genuinely closed. That is simply how rigorous, careful science works when the stakes of getting it wrong are this enormous. The downside of claiming too much too soon, of announcing a discovery that turns out to be wrong, damages scientific credibility in profound ways. It wastes resources as other teams spend time and money pursuing false leads. But the downside of dismissing a genuine discovery out of excessive caution is equally significant. Imagine if a skeptical community had dismissed the detection of gravitational waves when it first appeared on the horizon, or if they'd been too cautious about the existence of planets around other stars. The scientific process requires both boldness in pursuing genuine mysteries and caution in verifying claims. K218b reminds us that finding that balance is genuinely difficult, and that's exactly how it should be.